Natural rubber is one of Sri Lanka's most important natural resources. We begin a journey into the world of natural rubber, driven by academic curiosity to understand rubber cultivation and manufacturing. Located in the scenic hills of Wagga, Halpe Estate, managed by Pussalawa Plantation Private Limited, plays a significant role in Sri Lanka's rubber industry. Raw latex is carefully processed and transformed into essential polymer products used in everyday life. This documentary explores the journey of natural rubber, from the plantation to the final stages of manufacturing. History of Sri Lankan natural rubber manufacturing. On 12 August 1876, the Colonial Office, on the recommendation of Sir Joseph Hooker, sent 1,919 rubber seedlings from Kew Gardens to Ceylon. Grown from seeds collected by Sir Henry Wickham in Brazil, the seedlings were planted at the Henarath Goda Botanical Gardens under George Thwaites,
where successful growth led to further distribution across Singapore, Malaysia, India, and Burma. By the early 20th century, rubber cultivation expanded rapidly in Ceylon, turning it into a major center for rubber production in the region.
Rubber plantation. The rubber plantation, the journey begins with the creation of a germination bed. In the wet zone, seeds are sown around August and September, while in the dry zone, the ideal months are February and March. These seeds are carefully planted in the germination beds and nurtured until they sprout. Once the seeds have sprouted, the young plants are transferred into polythene bags in a dedicated nursery. Here they are nurtured for about 3 months, thriving under careful attention until their trunks reach a pencil thickness. Planting typically begins in the rainy season, around May and June. The monsoon ensures that the young plants receive ample water, making it easier to establish them in the field without the need for individual watering.
Maintaining correct spacing between trees is essential for healthy growth and efficient tapping. In Sri Lankan plantations, rubber trees are commonly planted at a spacing of approximately 3 meters by 6 meters, or in some estates 4 meters by 5 meters, depending on terrain and management practices. This spacing provides sufficient sunlight, airflow, and space for root development. Proper planting and spacing not only promote uniform growth, but also ensure easier movement for tapping operations and long-term productivity of the plantation. The lifespan of a rubber tree is generally around 30 years, divided into 2 main phases. The first 6 years are considered the immature phase, and once the tree matures, it enters the productive tapping phase for the remaining years. Before the tapping process begins, rubber trees must be properly prepared. Tapping is started only after the tree reaches maturity, usually after 6 years, when the trunk has achieved the required girth. Generally, a rubber tree is considered suitable when its girth reaches about 50 centimeters, measured at a height of around 1.25 meters from the ground. A field is officially declared a mature field when 60% of the trees in that specific block have reached the required girth, which is 20 inches. At this stage, tapping panels are carefully marked on the trunk. The first tapping panel is marked at a height of about 120 to 150 centimeters from ground level. This height ensures comfortable tapping for workers and allows efficient latex flow. Each rubber tree is divided into several tapping panels, commonly known as Panel A, Panel B, Panel C, and Panel D. Each panel has a durability of approximately 6 years, depending on the tapping system and proper management. After completing one panel, tapping is shifted to the next panel in sequence. This rotational use of panels helps prevent overexploitation, maintains tree health, and ensures long-term latex production throughout the economic life of the rubber tree.
Collection and preservation of latex.
After the early morning tapping, latex flows from the incision into collection cups attached to the tree trunks. Tappers carefully gather this milky liquid within a few hours and bring it to a central buying center within the estate. At the buying center, the latex is measured, inspected, and purchased by the factory or middlemen. However, payment to tappers is not based solely on volume. Instead, it depends on the dry rubber content, DRC, which represents the actual amount of solid rubber present in the latex, excluding water. To determine DRC, a small sample of latex is taken. Typically, 33 milliliters of latex is mixed with 66 milliliters of water to create a uniform sample. A Metrolac instrument is then placed into the mixture to measure its density. The Metrolac floats in the liquid, and the reading is noted from the instrument scale. This density value is then checked against a reference chart at the buying center. According to the chart, the measured density is multiplied by 30 to calculate the DRC weight, which indicates the actual amount of usable rubber in the latex. This value is used to determine the payment to the tappers, as it reflects the quality and yield of their work.
Once the latex passes these inspections, it is preserved with sodium sulfide and transported safely to the factory, ready for filtration, coagulation, and conversion into high-quality rubber sheets.
Chemical treatment of latex. Once the latex has been collected, carefully measured, and its quality verified, it enters the chemical treatment stage. This stage is essential to protect the latex, maintain its quality, and prepare it for controlled conversion into solid rubber. The first chemical added is Nexobleach, new formula, water-soluble. As a natural material, latex is highly susceptible to bacterial growth, which can cause spoilage, unpleasant odors, and premature coagulation. Nexobleach acts as a bacteriostatic agent, effectively controlling bacterial activity without damaging the latex. Its water-soluble nature allows it to disperse evenly, preserving the latex in a fresh, fluid state, while maintaining its natural flow and quality. The second chemical used is oxalic acid. Oxalic acid plays a stabilizing role in latex treatment by preventing premature coagulation during storage and handling. It helps maintain uniformity within the latex and ensures that coagulation occurs only at the intended stage of processing. This controlled stabilization is crucial for producing rubber with consistent texture and properties. The third and most critical chemical is formic acid, typically used at an 85% concentration. Formic acid is responsible for coagulation, the process that transforms liquid latex into solid rubber. When added in precise amounts, it causes the suspended rubber particles to bind together smoothly, forming a uniform and elastic rubber mass. Careful control of formic acid concentration is essential, as insufficient acid slows coagulation, while excess acid can result in brittle or uneven rubber. Through the combined action of these chemicals, the latex is protected from spoilage, stabilized during handling, and prepared for controlled coagulation.
Coagulation process. After the latex has been purchased, preserved, and treated with the required chemicals, it enters the coagulation stage, the critical step where liquid latex is transformed into solid rubber. At the factory, latex from different tappers is first collected into a large mixing tank. This ensures that latex from various sources is blended into a uniform mixture, achieving consistent rubber content throughout. Mechanical paddles are then used to stir the latex thoroughly. This mixing not only distributes the rubber evenly, but also removes air bubbles, which could otherwise cause weak spots or uneven coagulation in the final rubber sheets. Once the latex is well mixed, formic acid is carefully added. The acid initiates coagulation by causing the suspended rubber particles to bind together and gradually form a solid mass. After the initial reaction, the latex is transferred into smaller coagulation tanks. Dividing the latex into these tanks ensures that coagulation occurs evenly and efficiently, and makes it easier to handle the rubber slabs in the next processing stages. Inside the smaller tanks, the latex is left undisturbed for a set period, allowing the liquid to slowly solidify. During this time, the rubber particles come together to form solid slabs, while the watery serum naturally separates and rises to the surface. By the end of this process, the latex has transformed into uniform, high-quality rubber slabs, ready for rolling, drying, and further processing.
Milling and rolling process. After coagulation, the solid rubber slabs are carefully removed from the tanks and moved to the milling and rolling stage, a crucial step for cleaning, shaping, and improving the rubber's quality before drying. The rubber slabs are first fed into milling machines equipped with two heavy rotating rollers. As the rubber passes through the rollers, strong pressure is applied, which squeezes out excess water, removes dirt and impurities, and softens the rubber. Repeated passes through the rollers gradually make the rubber thinner, wider, and more uniform, enhancing its texture, flexibility, and workability. At the beginning, the rubber passes through grooved rollers, also known as creeping or washing rollers, while a continuous water spray flows over it. The purpose of this stage is to clean the rubber thoroughly, remove residual serum and acids from coagulation, and prepare the sheets for further processing. Second and third passes. The rubber is kneaded by the grooves while water continues to wash away remaining impurities. By now, the sheets are cleaner, softer, and more uniform, though the surface may still be ribbed. Fourth and fifth passes. Almost all remaining serum has been removed. The rubber is now smooth, flexible, and evenly crept, ready for finishing. The water spray plays multiple key roles during milling. It prevents the rubber from sticking to the rollers, washes away impurities, and controls the temperature, protecting the rubber from heat damage. After cleaning, the rubber passes through smooth rollers, also called finishing or sheeting rollers. By the end of this stage, the rubber emerges as clean, smooth, uniform sheets, ready for the drying process.
Drying process. Once the rubber sheets have been properly milled and rolled, the next critical stage is drying. Even after coagulation and washing, the rubber still contains residual moisture, which must be removed to ensure the rubber's stability, durability, and resistance to spoilage. There are different methods of drying used in Sri Lankan rubber factories and estates. Air drying. Sheets are hung in well-ventilated areas, usually on rails or racks, allowing moisture to evaporate naturally. Air drying is gentle and preserves the elasticity and natural colour of the rubber, but it takes longer and depends on weather conditions. Mechanical or oven drying. In some factories, heated air or mechanical dryers are used to remove moisture more quickly. Temperature and airflow must be carefully controlled because excessive heat can harden the rubber, reduce elasticity, or cause cracking. During drying, sheets are regularly turned or spaced to ensure uniform drying. The goal is to reduce the moisture content to the optimal level for storage, typically around 10 to 12%, while preserving the rubber's flexibility, tensile strength, and natural properties. Proper drying is crucial because over-dried sheets become brittle, while under-dried sheets remain vulnerable to microbial attack or shrinkage during storage.
Grading and packaging. Every sheet is examined under strict quality standards, and any defects are removed to ensure uniformity. The graded sheets are then organized and formed into standard weight bundles. These bundles are passed through rolling machines to refine thickness and surface consistency, ensuring the rubber meets precise specifications. Next, the rubber is accurately cut to size, maintaining consistency while minimizing waste. The finished sheets are then sealed in protective packaging and compressed, reducing volume and safeguarding quality during storage and transport. The industry also produces a range of secondary products that maximize resource utilization and reduce waste. Low-grade sheets, or scraps, from the main processing line. Scraps from smoked or low-grade sheets, as well as off-grade coagulum, are reprocessed into block rubber, crepe rubber, or latex foam. These secondary products are widely used in mats, shoe soles, hoses, gaskets, and other industrial applications. Even small pieces of leftover rubber are carefully collected, cleaned, and remixed to ensure minimal waste and maximum value. Liquid byproducts, such as latex serum or diluted latex, are also utilized to produce latex concentrate or compounded materials, which feed industries like footwear, tire production, and dipped goods manufacturing.
Wastewater management. After rubber processing is completed, proper wastewater management becomes a vital part of factory operations, ensuring environmental protection and regulatory compliance. Water used during milling, rolling, equipment cleaning, and chemical treatment generates wastewater containing latex residues, acidic substances, and traces of processing chemicals. At the Halpe Estate Rubber Factory, all wastewater is directed into a dedicated treatment system. Initially, it is collected in treatment tanks, where solid particles and rubber residues are allowed to settle, reducing suspended solids. The pH level is carefully monitored and adjusted to remain within a safe range of approximately 6 to 8, ensuring environmental safety. Additional quality parameters are checked to meet required standards.
From the first drop of latex collected at dawn to the final rubber products ready for use, every stage of processing reflects care, precision, and responsibility. At Halpe Estate, natural rubber production goes beyond manufacturing. Quality control, proper preservation, and safe wastewater management ensure that both the product and the environment are protected. This journey shows that sustainable rubber processing not only about production, but about respecting nature while meeting human needs.